I'm Umberto Battino. I will be the host of this seminar. I'm currently talking to you from the UK, from North Yorkshire. I'm a postdoc at the University of Hull, and I'm involved in stellar modeling and nucleosynthesis calculation. Especially, I'm very keen on stuff like the S process, transiron nucleosynthesis, and AGB stars in particular, and type 1a supernova progenitors. But actually, then more often than not, I'm also involved in any kind of stellar object. I'm here basically, it's quite a pleasure to me to introduce this speaker, today's speaker, who is Daniele Gasparri. He's currently a postdoc at the University of Atacama in Chile. So briefly, just a brief information about him. So he graduated in astronomy and astrophysics at the University of Bologna. He got his PhD at the University of Atacama. Right now is a postdoc at the University of Atacama. He's also very, very involved in the science communication and public engagement. And also he's an official photographer of ESO. He's an ESO photo ambassador. The picture you see here and as like the cover picture of his talk is actually picture taken by Daniele himself through his amateur telescope from the Atacama Desert. So this is the kind of stuff he's also keen to do. So concerning his research, he started off on basically studying extrasolar exoplanet, but then from the PhD on, he focused his attention on unresolved galactic stellar population from the observational point of view. And today we'll hear him talking about new near-infrared spectroscopic indices of unresolved stellar population. So, Daniele, you can start whenever you're ready. You have 45 minutes. I'll tell you when five minutes are left. So.
Thank you very much, and thank you for the invitation. So, in this seminar, I'm going to introduce my work, which is a work I started during my PhD and still going on in my postdoc fellows. It's a work focused on the study of unresolved stellar population, which means basically galaxies. So from the observational point of view, my work was, the goal of my work was to find a new spectroscopic indicators. Now we'll see briefly what are these indices. Find a new spectroscopic indicator in the spectra of the galaxies in the near-infrared regions that can be used to constrain the properties of the stellar population of galaxy, which are basically age, metallicity, alpha enhancement, and maybe also the stellar mass, the kinematics of the galaxy, and the IMF, which is the initial mass function. So this is a very, very brief introduction. This is the outline of my presentation. We'll see a little more about the stellar population and what are these spectroscopic indices. Then I will present my work. So the goal of my work is to find spectroscopic indices in the spectra of the galaxy which are sensitive to the properties of the stellar population. So the first step is to define new spectroscopic indices in the near-infrared region, because the focus of my work is in the near-infrared region of the spectra from 0.8 to 2.5 microns. So we start by defining and testing new indices for the stars. Then we apply this new index system for a first sample of galaxies. Then, if everything goes well, and of course, everything went well because I'm here to present this work to you. In the third step, I will use a larger sample of galaxies to define new age, metallicity, and velocity dispersion indicators. So basically, by measuring this line or lines in the near-infrared regions of the spectra of the galaxies, we'll know the age, the metallicity, and the velocity dispersion, and maybe some information about the IMF of the galaxies. Then I'll explain. I'll make my conclusions. And I talk briefly about the future work that can be done. So let's start from the beginning. What are the galaxies? What are galaxies? Maybe I hope everyone knows what is a galaxy. Well, a galaxy is a very complex system made of gas, dust, and hundreds of billions of stars, if we consider only the baryonic matter. And the galaxies are among the most ancient structures in the universe. They are present up to very high redshifts. I think this is a new field because the James Webb Space Telescope is discovering every day galaxies farther away from us. From the observational point of view, from the near ultraviolet to the near infrared region of the spectra, the galaxy, the light of the galaxies is dominated by the stellar content, by the stars. So very open questions about galaxies is how they form and how they evolve. So the formation and the evolution of galaxies is a very open and still unknown topic. Without going further, there are two main scenarios to the formation of galaxies. The first scenario is an early monolithic collapse of a giant cloud that form the bulk of the stellar population. Then there is a secular evolution made by minor and major merging events. These can be dry merging or wet merging, considering the amount of gas and stars that are in the galaxy that we collide. So the main point is that we don't know much about the formation and the evolution of galaxies. So the question is, how can we contribute to the knowledge of galaxies? One way is to study the stellar population of galaxies, because the stars, they trace the formation and the evolution processes of the galaxies. So age, metallicity, alpha enhancement, mass distribution, and also the kinematics are the key ingredients to discover the complex history of the galaxies. And this data is written in the stellar content on the galaxies. It's wonderful. So to know all about the stellar content of the galaxies, we just need to study the stars. So we can observe the single stars one by one. Maybe it's a little time-consuming task, but we can do it. No, because there is a very small or big problem. Besides a few galaxies located mainly in the local group, we cannot see the single stars of the galaxies. So we cannot study the single stars like we do, for example, for the Milky Way. That's why we talk about unresolved stellar population. So stars that we cannot see one by one, we cannot resolve. So the following question is how we study the unresolved stellar populations. Well, through the so-called integrated spectra, which is the spectra containing the information of billions of stars weighted by their luminosity. When we put a slit in this image, we can see we put a slit through the central region of a galaxy. We see the spectra on the right. We see the spectra combined of all the stars contained in the slit, weighted by their luminosity, which is, for example, AGB giant stars will dominate in light with respect to the dwarf star, or a star like our sun. But the main point is that the information that we need about the stellar population of galaxies and their properties is contained in the integrated spectra. So we just need to extract this information. We cannot see the single star, we see millions of stars together in the spectra. We need to extract the information we want from this spectra. The information is the properties of the dominant in luminosity stellar population: age, metallicity, alpha enhancement, IMF, if we are lucky, and we'll see we are not so lucky, but this is the way. So there are two methods to extract the information about the stellar content in the spectra of the galaxies. The first one, I called it the cool method. It's called officially the full spectral fitting, which is a really new method. We are applying the full spectral fitting only for 15, 20 years. The idea is simple. We fit the spectra or a region of the spectra, usually the optical part, with a combination of simple stellar population templates. So we have a group of templates. There are codes like the PPXF code of Capellari, which is the most used code for full spectral fitting, and the code magically gives us the information about the stellar population of the galaxies and also about the kinematics. So we have everything. It's very cool actually, because now this code of Capellari is very, very stable and very easy, well, quite easy to run. There is also the other method. It's called the old school method because it's a method developed since the 70s of the 20th century, which is focused on finding some indicators, some absorption line in the spectra sensitive to the properties of the stellar population. So this is the idea of a spectroscopic index. A spectroscopic index is just an absorption line which is sensitive, we know, is sensitive to a variation of age, metallicity, alpha enhancement, which is sensitive to a variation of stellar parameters or structural parameters. So we define an index with a band on top of the line we want to measure. We will measure the line, the intensity of the absorption line through the equivalent width. The equivalent width, maybe you know, is just the area, the surface of the line. This equivalent width is measured with respect to pseudo-continuum level. You can see in this image, a pseudo-continuum level which is determined by two pseudo-continuum bands, one on the left and one on the right of the line we want to measure, which are usually close together. So from these two bands, on the blue side, on the red side, we measure the continuum level, and then we measure the equivalent width of the line with respect to this continuum level. This is the idea of an index. We measure, when I say I measure an index, I measure the equivalent width of an index, I mean that I measure the intensity, the area of this absorption line. Of course, this is not a new idea. I didn't invent anything, because one of the most reliable and used system of spectroscopic indices in the optical is the LIC-IDS system. It's a system of 20 to 25 indices in the optical band, which are mainly sensitive to the structural parameters of the galaxies, which is basically they are sensitive to the properties of the stellar population of galaxies. From this group of the index, there are a small group which is still used, is still very useful to constrain the property of the stellar population of galaxies in the optical. Here we see the two index diagrams. On the left, we see the H beta index, which is considered an age indicator. The H beta in galaxies is mainly sensitive to age, versus a composite index of magnesium and iron, which is mainly sensitive to metallicity. So if we correlate these two indices, one sensitive mainly to age, one sensitive mainly to metallicity, we put our point, the black point are the equivalent width of H beta and mg Fe of the galaxies, and we built the grid, the blue grid, from the models of the simple stellar populations. So we put the points, we put the models of simple stellar populations. We can constrain the age and the metallicity of our galaxies. You can see from here. On the right, it's a different index to index diagram where we have a magnesium index and an iron index. This diagram is used to constrain the alpha enhancement, because the iron is sensitive only to iron abundances, while the MGB is the magnesium is an alpha element. So with these two indices and the model grids, so the simple stellar population models superimposed, we can constrain the alpha enhancement of our galaxies. So these are the holy grail of the a system of index. This is very useful in the optical, which is very powerful instrument. Okay, it's not so powerful like the cool method of the full spectral fitting, but in some ways is more reliable. Why? Because the cool method is cool, but has some issues, especially in the near-infrared, which is the main focus of this seminar, the main focus of my work. In order to perform a good fitting of the spectra with a set of stellar templates or simple stellar population templates, we need, of course, a very good flux calibrated spectra without continuum distortion. This is very difficult to achieve, especially in the near-infrared. We see the circle there around 2.2 microns, which show a bump just before the CO overtones. This bump is not real. So in this case, if we perform a full spectral fitting of the spectra, we don't have reliable results. We have more because especially in the near-infrared, we have a lot of sky emission lines and a lot of telluric absorption due to our atmosphere. So the problem is, in order to perform a good full spectral fitting, we need clean spectra. We need to correct for the sky emission and for the telluric absorption. And this is a very, very difficult task in the near-infrared. Then we have some other problems. For example, we need to correct for the extinction by dust, which can be tricky in the near-infrared because it's a very wide region of the spectra, and a good full spectral fitting requires very high signal-to-noise spectra. We are talking about signal-to-noise around 100 per pixel, which is very high for galaxy spectra. So for this reason, for these difficulties, I did not follow the cool method. I focused my work into the spectroscopic indices approach. Of course, in the optical part, the spectroscopic indices have some issues. Otherwise, you can ask, why did you focus by looking for spectroscopic indices in the near-infrared when we have a system of indices in the optical part of the spectra that works perfectly, because it doesn't work perfectly. For example, in the index diagram, H beta and Mg iron, you can see that the H beta and also the composite in the index Mg and iron are sensitive to age and metallicity. In the optical part of the spectra, this is a well-known problem. There is the so-called age metallicity degeneracy. So basically, this means that we cannot recognize a variation of age or a variation of metallicity. With the leak IDS system, we can separate the contribution of age and metallicity within certain boundaries. For example, you can see for that for low values of Mg Fe, the model grids are overlapping. This means that the points that falls in this region, we cannot say their age or and their metallicity. We cannot disentangle age and metallicity. They are degenerate. Then the leak IDS system has some other problems. For example, has been developed on low resolution spectra. This means that many lines, including the H beta, are contaminated by other lines because the index definition, because the low resolution has very wide bands. Then is sensitive, this index system is very sensitive to extinction because we are working in the optical part of the spectra. And you know that the optical part of the spectra is very sensitive to dust extinction. So this system has some problem, but there are other problems that I will discuss in the next slide, because the question is, what about the near-infrared? The problem of the leak system is that is just in the optical part, but all the future telescopes and also some of the most recent telescopes, for example, the James Webb Space Telescope, are working and will work in the near-infrared region of the spectra. So the leak IDS system for this telescope, for these instruments, is not useful because we don't have the information of the spectra in the visible part. So that's why the near-infrared, between 0.8 and 2.5 microns. This is a complementary band with respect to the optical that allows us to see other stars, because in the near-infrared, especially in the H and K bands, we see mainly AGB and RGB stars. We don't have information of main sequence turn-off stars. We have a lot less extinction, so the investigation of near-infrared galaxies will allow us to see where the optical part cannot see. I'm talking about the dust obscured galaxies, which can be investigated in the near-infrared regions. Last but not least, I already said, all the future telescopes will work in this range. So we need an instrument to unveil, to constrain the property of the stellar population of galaxies without the optical part. Because also the full spectral fitting in the Cool method is working well only in the optical part. No reliable information are present in the near-infrared region. This is actually the status of the investigation in the near-infrared region before I started my work. The full spectral fitting was not reliable and is still not reliable in the near-infrared region. If you are curious, just run the PPXF code on Galaxy Spectra, selecting the spectra in J band, and in the K band, the code will give you very, very different results. Like if there are two galaxies completely different. So the full spectral fitting in the near-infrared is not reliable. The index study in the near-infrared has been not complete. Some indices have been identified, for example, the calcium triplet lines, which are very famous and very used since, I think, 20 years. We know some indices in the K bands, the sodium, for example, in the K bands, that is a nightmare for some people, especially for those that are developing the theoretical models. But there are a lot of absorption lines that are still not studied, that were still not studied until my project started. Because the main problem until 5 to 6 years ago were two. We had two problems. We had a relatively low resolution spectra of galaxies, and we were lacking of reliable stellar libraries in order to define the new indices, because in order to study and define new spectroscopic indices to use for galaxy, we need to start from the stars. But if we don't have reliable stellar libraries, we cannot say anything. So now we talk about my work and my findings. The first step I did was to collect the most recent stellar library to define new spectroscopic indices in the Y, J, and H bands. My work was following the work started by Cesetti in 2013. So in this band, I was looking for absorption lines sensitive to the stellar parameter, to a variation of stellar parameters. Now we are talking about stars, so we are not talking about age. We are talking about temperature, metallicity, and surface gravity. Here we are. So I collected almost 800 stellar spectra spanning a wide range of temperature, metallicity, and surface gravity. A very useful library was the X-Shooter library, released just at the beginning, just 1 year after the beginning of my PhD. Here you can see the distribution of the stars in temperature, metallicity, and surface gravity. You can see that thanks to the X-Shooter library, which is the gray histogram, we have a very wide parameter coverage in temperature, in metallicity, and surface gravity. So we can test our spectroscopic indices over a very wide range of parameters. Then, once I had the stellar spectra with very known temperature, metallicity, and surface gravity, I built the so-called surface sensitivity maps. So basically, I made the derivative of the spectra with respect to one of the 3 considered parameters in order to find which are the most sensitive absorption lines to be investigated. Because in the near-infrared, we have hundreds of lines, but only the strongest, the not contaminated, and the most sensitive to the stellar parameters are worth to study. So through these sensitivity maps, I recognized the lines sensitive to a variation of stellar parameters. For example, here we can see the Paschen beta lines, which is not the line, this is the derivative of the Paschen beta. You can see there is a spike going down on the spectra because the Paschen beta lines for different spectral types, which is for different stellar temperatures, is very sensitive. So we have a variation very large. So for example, the Paschen beta line is a very useful line to be used as an index. Once I recognize the lines, I fixed the index band, especially on the pseudo-continuum, by looking for derivatives, in this case, where there are no peaks. So the index is the line, an ideal index is a line with a very high peak in this derivative plot. Pseudo-continuum band, where I put the continuum in order to perform the equivalent width measurement of the line, is where I don't have peaks. So here I identified all the indices. And this is the results. 60 new indices are integrating the work of the Cesetti in 2013 in I and K bands. So in the whole near-infrared region, we have 75 indices, 44 atomic metal indices, 17 hydrogen, and 14 moleculars. And this is these are the results on the stars. Basically, the most sensitive indices are in the J and the H bands. The hydrogen indices, of course, are very sensitive to temperature, like in the optical, and little to metallicity, while the metal and the molecular indices are sensitive basically to the three considered parameters. So it's the degeneracy between three parameters: metallicity, surface gravity, and temperature. So in order to define indices, metal indices sensitive only to metallicity and mainly to surface gravity, I also defined two composite indices that can be used actually to measure the metallicity of the stars, especially the Z1 index. You can see in this image the Z1 index, the equivalent width, is not sensitive to the temperature. On the left, we have a flat group of stars, is very sensitive to metallicity, almost linear, and is almost not sensitive to surface gravity. On the right, you can see this is the only index for stars which is sensitive only to metallicity. The other index, the G1 index, is on the other hand very sensitive to the temperature on the left, but also to the surface gravity on the extreme right. You can see that the giant stars have a very high equivalent width than the dwarf stars, which are the stars with log G around 4 or 5. So this index can be maybe used to constrain the initial mass function of the galaxies, because it's mainly sensitive, it shows a very large sensitivity to surface gravity. So this is the index system to the stars. We see some indices are very sensitive to temperature, metallicity, and surface gravity. So now we need to apply this to the galaxies. The first step, which is the second step is to test this new system of index to a preliminary sample of galaxy. For this, I published the paper in 2021. For this task, I used the observation of the central regions of 14 galaxies made with the spectrograph X-shooter of the very large telescope, with a very high resolution for a galaxy spectra, around 5,000, from the near ultraviolet to the near infrared. The galaxies, the preliminary galaxy sample is very heterogeneous in morphological type. Here in the table, you can see some basic infos. We have elliptical S0 and spiral galaxies. The only small range is metallicity, which is more or less around solar metallicity and a little supersolar, spanning all the age from 0.8 to 15 gigayears. So this preliminary sample of galaxies is the perfect test to transform, to make the transition from pure stellar indices to galaxies indices, and to see if and what indices are really sensitive to galaxies. This sample of galaxies is well known. You can see here also the age, metallicity. So this is basically a calibration sample. In order to perform the indices measurement for galaxies, we need to adjust a little with respect to the stars. For example, we need to correct the spectra for the Doppler shift. We need to have the spectra all to the rest frame. We measure the index, the equivalent width, just like for the stars, but we need also to correct for the effect of velocity dispersion. The velocity dispersion broadens the line and usually lower the equivalent width. So we need to apply some coefficient, some correction coefficients for the galaxies in order to have measurement done like the galaxy has zero velocity dispersion. So once we have the Doppler correction, the index measurement, and the correction from the velocity dispersion broadening, we can correlate these indices with the parameters of the stellar population of a galaxy: age, metallicity, velocity dispersion, and so on. So the result of this first step is that only 40 of 75 indices are suitable to be measured in spectra, in galaxy spectra, because many of these indices fall in the telluric absorption, and the spectra of galaxies have much less signal to noise than the stellar spectral libraries used. Generally, we don't see differences in morphological types. The only difference due to the morphological types is that in this sample, and generally, the elliptical galaxy, the early type galaxies, are very old systems, so they tend to have smaller equivalent width values of hydrogen indices and larger for metal indices. Many indices, this is a very interesting point, are correlating actually with the velocity dispersion, with the central velocity dispersion of the galaxy. The calcium triplet lines are the only indices that anti-correlate with the velocity dispersion of the galaxy. This is a very known anti-correlation, which is very studied and very few understood until now. And I did not understand still. So speaking of some indices, there are a small group of the indices, especially the Pesce beta, for example, that show very high correlation with the H beta. We know that H beta is an age indicator. So if the Pesce beta correlates with the H beta, we know that maybe the Pesce beta can be used in the near-infrared as an age indicator. So this is maybe a potential age diagnostic. Then we have a very small group of indices, mainly aluminum, carbon CO indices, and FEH index that do correlate with the leak indices used as stellar population diagnostic. Do you remember the index to index diagrams? we used basically a magnesium, iron, and a combination of magnesium and iron indices. So the idea is that if we have near-infrared indices that do correlate with these indices that are used in the optical part to constrain the properties of the stellar populations, so we are confident that these new near-infrared indices can be very good potential metallicity indicators in the near-infrared. The problem is that we need more data, and the more data are here. So in the third and last step, I defined, I used as an enlarged sample of 32 galaxies. You can see here the distribution in sigma, in morphological type, in age, and metallicity. All these new galaxies were observed, or we retrieved the spectra in literature with X-shooter, with the same constraint of the preliminary 14 galaxy sample. So now we have 32 galaxy spectra. Remember, the center, only the central region of the galaxies. We need to find if there are new indices suitable to determine age, metallicity, alpha enhancement in the near infrared. How we do that? So the basic idea is to use also the simple stellar population models. Then, with the aid of simple stellar population models, we generate combined indices that can maximize the correlations with age and metallicity. Then, if we are lucky, spoiler alert, we are not lucky, we will use the simple stellar population model to fine-tuning this new age and metallicity diagnostic. The first indicator I found in the near infrared is a velocity dispersion indicator, which is called sigma 1. You can see on the right. This sigma 1, which is a combination of magnesium, aluminum, and calcium lines, shows a very high correlation with the central velocity dispersion. This is basically a mass indicator, like the Mg2 index used in the optical part. So by measuring this index, we can see, we can retrieve the velocity dispersion, the central velocity dispersion of the galaxy. And since we know that there are connection between the central velocity dispersion and the mass of the galaxy, we can also have a rough estimation of the mass. Then I compared the data, the equivalent width of the galaxies, of the index of the galaxy, with the simple stellar population models. I used two models, the E-miles models of 2016 and the new X-shooter models. The problem is in this slide. You can that, especially on the right, where I show the Kolmogorov-Smirnov statistics, the models cannot reproduce well the equivalent width of many indices. So, especially for the metal and molecular indices, the models cannot reproduce the data. So we cannot use basically the models to build the spectroscopic indicators we want to build in the near infrared. So we try a different approach. The different approach is to compare the new near infrared indices with the optical indices for galaxies and models. So we have a basic idea of the correlations involved. We select the indices that most correlate with the LIC IDS opticals, and we start from here to build some composite indices. Here we have an example. For example, the index of interest are the Paschen beta, the magnesium, and basically the aluminum. So from these indices, I just played just made some combination to maximize the correlation with the index used in the optical part of the spectra as stellar population diagnostic. And the results are here. For example, the aluminum index, L star index, is very sensitive to the magnesium. So the aluminum star index in the near infrared is the alter ego of the magnesium indices in the optical part. Very sensitive to alpha enhancement. While the composite index alpha, you can see the definition here, is very sensitive to the composite index MGFE. This composite index is used as metallicity indicator. Okay, here you have the calibration between the optical indices and the near infrared indices. So this is the potential metallicity indicator. Here we have the potential age indicator. Let's see, the patient beta is not a good metallicity, is not a good age indicator, because the correlation with the age indicator H beta is high, but you can see a separation here in metallicity. So I defined a new index, the T1, made with a combination of near infrared indices to minimize this scattering due to the metallicity and tighten the correlation with the age indicator H beta. So now we have the candidate of age indicator. We can see here, if we do correlate the T1 with age in the bottom panel, we see a very clear trend with age. So the T1 index is the strongest age indicator that I found in the near infrared. On the right, you can see that the correlation with the metallicity is very scattered, so we don't have a trend with the metallicity. For the metallicity indicators, I selected two indices, the alpha and also the cat-al index. You can see it. They are very sensitive to metallicity on the right and show a little sensitivity to age, only the alpha index on the left. For the last part of my work, I compared the models and the points by building the model grids. On the left, you can see the H beta and MG iron index used for X-shooter and E-miles models. You can see the points are overlapping the data. At the center on the right, you can see the H beta and the new metallicity indicators that I found on the near infrared. You can see that the alpha index is pretty the same of the MG iron index in the optical. It's
5
basically
minutes.
Sorry?
5 minutes.
Perfect. So on the right, you can see that also the index cat-al, which is a combination of calcium triplet lines and aluminum, can break very well the age metallicity degeneracy. So the index cat-al is not sensitive at all to age. This is the first index that we found, even in the optical, that show no sensitivity at all to the age, only to metallicity. So this is pretty interesting. Although you can see, okay, you can see that the distribution of the galaxies is a little more scattered. While in the central diagram, in the central plot, you can see that the most metal-rich galaxies, which are the darkest red point, are on the right, and the low metallicity galaxies tend to be on the left, where they should be, considering the model grids. For the calcium index on the right, we don't have this separation. I think, this is my guess, that the calcium abundances on the galaxies, the different calcium abundances on the galaxies, that they skew the distribution of metallicity. So maybe we need to just fine-tune this index by introducing another, maybe not an alpha element, maybe an iron element, because it's very interesting because we don't have the dependency of age. The problem arises when we substitute the T1 to the H beta because the models explode. The models, especially the X-shooter models, have some problems to parameterize the equivalent with the absorption line of the Paschen beta line. I don't know why. They become degenerate. They have a very different behavior with respect to the E-miles model, and I don't know the reason. So the conclusion of this analysis is that the models still cannot be used to retrieve the information of stellar population in the near infrared. Just a hint of just to stimulate your curiosity, I defined 4 indices that, according to the models, the E-miles models are sensitive to IMF variation. You can see here different exponent of the IMF foresee very different equivalent width, especially for the G1 index on the left. It's a shame that the galaxies do not overlap to the data. So we still don't have the instruments to see if there is a variation of the initial mass function in the galaxies or not. So the conclusion of this work is that in the near infrared region, at last, we found new velocity dispersion indicator, a new metallicity indicator, at least 1, maybe 2, a new age indicator, which is important because until now, every study failed to find an age indicator in the near infrared. Unfortunately, the other conclusion is that the SSP models, even the newest simple stellar population model, still need a fine-tuning because they are not still overlapping with the data. But of course, the near-infrared indices are very useful, and we can also use the indices now because the empirical calibration I presented before can allow us to measure the near-infrared indices, for example, only if we have the near-infrared spectra. We can constrain, we can retrieve the information of the leak IDS systems used as stellar population diagnostic, and from there, use the models to constrain the properties of the stellar population. So we are waiting for the models to be self-consistent in the near infrared, but in the meantime, we can use the empirical calibration given to measure the index in the near infrared and retrieve the index in the optical, and then from there, retrieve the information on the stellar population of the galaxies. So the future work is focused on the 2 points. One is to enlarge the sample of galaxies, which is my part, and the second part is maybe someone someday will be good enough to build some models that can parameterize correctly the yield of the AGB stars in the near infrared region in order to better reproduce the data. So this is all. Thank you very much.
Thank you, Daniela. Very nice talk.